All right, so this video is going to be going over how we actually find area. So since R is defined by the angle from the pole, or the zero, to all of these pieces, we have to think about, like before when we did area and we started with like a Riemann sums kind of approach, right? Where we like broke up the area that way. Well, that's because like our delta x was along the x-axis. Well, now our delta theta is a change in the angle, okay? So we're still going to have this change in theta that's like, okay, I need to go from alpha to beta in certain number of intervals, but these are now changes in the angle. And so these are going to be like little pi pieces that get cut along the way. And then the nice smooth area is if we let delta theta go to 0. Okay, so that's kind of how this will work. And if you remember back when we did area of a sector of a circle, it was a little piece of pre-cal. This was the formula that was used. And so we're going to use that exact same piece, but we're going to say, hey, add up each and every little piece of these. Mathematically, this is what we are doing. So we're saying, okay, add up each and every little piece of these, and then let delta theta go to 0, or take infinite number of those angles. And this is the formula that we're going to use. Now, in my classes, I'm going to give you this formula because applying it is more what I need to know if you can do. And so let's look at this example right here. Find the area of one petal of the rose defined by r equals 3 sine 2 theta. So sine starts at 0, so 0, 0 is my start. And then I have a radius of 3, and that's going to max out at, let's think about this, sine, okay, at pi over 2, but this is 2 pi equals pi over 2. So that's at theta equals pi over 4. I'm going to have, radius of 3, 2, 3. So one little loop-de-loop, and then I need to go back down here by pi. But again, if it's 2 theta equals pi, then really that's at theta equals pi over 2. So one lapse from 0 to pi over 2, I max out at pi over 4, and I loop back in. Then between pi over 2 and pi, my radius is going to be negative, so I end up getting this petal, okay? Here, I end up getting, I'm going to be like back around, right? Because this is sine of 2 theta, so these radii are actually going to end up being positive because I'm on this piece. And then I'm going to loop back up like this. Now I need to figure out the area of just one petal. So one petal of this rose is just from 0, so 1/2, the integral from 0 to pi over 2 of 3 sine 2 theta, because that's my function, that's my radius, squared d theta. What is that going to then give me? Let me put this down just a little bit. So that's going to give me 1/2 integral from 0 to pi over 2 of 9 sine squared 2 theta d theta. And then I need to use a half angle, or not half angle, sorry, a power reducing angle to get rid of my sine squared. So sine squared of alpha is 1 minus cosine of 2 alpha over 2. but I have 2 theta. So I'm going to take this 9 out, 9 halves, this integral, and in place of sine squared of 2 theta, I'm going to have 1 minus the cosine of 4 theta over 2. So 9/4 integral from 0 to pi of 1 minus cosine 4 theta d theta gives me 9/4 of theta minus 1/4 sine 4 theta from 0 to pi. Sine of 4 theta and sine of 0 are going to give me 0. And so the only one that's going to come into play here is my bounds. Okay, there we go. There we're fixed. Okay, so the only thing that's going to come into play here is pi over 2. I was looking at pi and I was like, that's not right, but pi over 2. So when I plug in pi over 2, 4 pi over 2, so sine of 2 pi, yes, still 0. So the only one that's going to come into play is when I plug in here. So 9/4 times pi over 2, or 9 pi over 8. Now, because I have 4 of them, if I wanted to figure out the full area, I could just multiply that by 4. It'd be 9 pi over 2. This said just 1 petal, though, so I'm going to just leave it there. All right, let's look at another example. So I want to find the area inside the cardioid defined by the equation 1 minus cosine theta. If I were to create a table here with theta and r just to see where this goes, when I plug in 0, I end up getting 0. So I'm going to start at 0, 0. When I plug in, let's just plug in pi over 4. I get 1 minus root 2 over 2. Which is 0.3. So pi over 4 is like only 0.3, so it's like little itty bitty. Let's do pi over 2. The cosine of pi over 2 is 0, so I'm at 1. And then let's go to 3 pi over 4. Now that's going to be 1 plus root 2 over 2. So 1.7. And then at pi, I'm at 1 minus -1. So 2. And then it's going to repeat that. So it's going to go around and then around again and be symmetric there. So I need the full, the reason I wanted to graph this out is I need the full like 0 to 2 pi, right? Like 0 to pi over 2 got me here, pi got me here, pi over 3, and then back around that way. So I need to do the integral 1/2 from 0 to 2 pi of r squared d theta. All right, inside here, that's going to be 1 minus 2 cosine theta plus cosine squared theta. And I'm going to have to use a reduction formula again for cosine theta, or cosine squared theta. And that ends up being 1 plus cosine of 2 theta over 2. Okay, so I have 1/2. And let's go ahead and integrate this. So 0 minus 2 sine theta plus 1/2 theta plus 1/4 sine of 2 theta. And I'm taking that from 0 to 2 theta. All right, I end up having 3/2 theta if I combine those. Sine of all the 0s and 2 pi's and all of that and 4 pi's, those are all 0. So again, I kind of luck out here that I just have a half and then times 3/2 times 2 pi. And so I end up getting 1/2 times 3 pi, or 3 pi over 2 as that area. All right, we have one more example here. I want to be inside r of 4 cosine theta, but outside the circle, r equals 2. Okay, let's just do a couple points on this 4 cosine theta. So 0, oh, darn it. When theta is 0, let's write that better. When theta is 0, r is 4. Okay, at pi over 4, I'm at 2 root 2. At pi over 2, I'm at 0. And that's going to loop around. So this is actually going to be the circle that loops around this way, like so. Okay, so inside that circle, but outside this one. Okay, so I want this area. Well, let's go figure out where these angles intersect. So where is 4 cosine theta equal to 2? Or where is cosine of theta equal to, divide by 4, 1/2. Where is the cosine of theta equal to 1/2? Well, that's at pi over 3 and negative pi over 3. So those are my bounds. Negative pi over 3 to pi over 3, 1/2 integral. Negative pi over 3 to pi over 3. And then you have to think about what this is. Like, what is my radius along here? This length is this value minus this value. So inside here, I have to do 4 cosine theta minus 2 squared. Okay, if I expand that out, I end up getting 16 cosine squared theta minus 8 cosine theta minus 4. Let's go ahead and take a 4 out of all of that mess and divide by 2. So I'm going to have 2 integral from negative pi over 3 to pi over 3 of 4 times 1 plus cosine 2 theta over 2 minus 2 cosine theta minus 1 d theta. So this is 2. 2 times 2 theta plus sine of 2 theta minus 2 sine of theta minus theta. Okay, minus theta plus 2 theta. So I'm just going to end up having 1 theta there from negative pi over 3 to pi over 3. Now we can also go from 0 to pi over 3 and double it, right? Because it would be that's exactly the same. So I'm just going to do that when I plug these in because sine of 0 is 0. So I'm going to double this. So I'm going to have to erase this up here. Okay, so we have 4 times pi over 3 plus the sine of 2 pi over 3 minus 2 times the sine of pi over 3. And then when I plug in 0, I just get 0, so minus 0. Sine of 2 pi over 3, 2 pi over 3 is root 3 over 2. And then minus 2 root 3's over 2's. So I just have minus 1 root 3 over 2. And then that's going to be my area for the whole shebang because I'm multiplying by 4, which is the doubles. So that should be good to go.